Hi everyone, my name is Cassey and I'm a research engineer from Quantum Communication Laboratory at National University of Singapore. So I would like to share about our work on the experimental proposal of discrete variable quantum key distribution with HOMODYNE detector. So QKD protocol can be categorized into two main categories. The first one is the discrete variable QKD protocol, or DV in short, and the second one is the continuous variable QKD protocol, or CV in short. So each of these protocol has their own plus and minus. So for example, for the source part, the DV-QKD protocol has the advantage that we don't need to share any phase reference, whereas for the CV-QKD protocol, we need to establish some phase reference between the signal and the local oscillator. For the detector part, the DV-QKD protocol uses the single photon detector that is relatively slow, bulky, and expensive, whereas for the CV-QKD protocol, it uses the HOMODYNE detector, which is relatively fast, small, and cheap. So in terms of performance, the DV-QKD protocol works well in the long distance regime, but it has a low speed. Whereas for the CV-QKD protocol, the distance is limited to metropolitan distance, but it has a high speed. So given the advantage and disadvantage of these two protocols, it is interesting to ask a question of whether we can combine these two protocols to leverage the advantage. So our group has proposed a hybrid QKD protocol that uses the source from the DV-QKD protocol and the detector from the CV-QKD protocol. And our protocol has the advantage of being more practical and also works well with high speed, and it works best in the metropolitan distance regime. So the idea of our work is that if we randomize the phase between the signal and the local oscillator, our HOMODYNE will work in the noisy photon counting mode, and by utilizing this feature, we can use the HOMODYNE detector to decode and learn the information from ELISA signal. So the first step of the protocol is the state preparation and measurement. So our protocol is based on the time phase encoding of BB84 protocol, and we also deploy the decoy state method. So Alice will choose her basis choice, her bit value, and the intensity level, and encode her signal accordingly and send her signal to Bob, and Bob will measure it. And then the next step is the basis and intensity announcement as well as the decoding. So Alice will announce her basis choice and the intensity choice, and Bob will assign some bit value to his measurement or according to Alice's announcements. And in here, we note that the basis selection is done on the post-processing layer, so this will reduce the complexity of our experimental implementation. And then the last step is the parameter estimation and the classical post-processing. So this is the simplified diagram of our experimental setup. So in Alice's lab, she will have some laser source to generate the signal, and also some intensity modulator and phase modulator that is controlled by arbitrary waveform generator to modulate the signal, and as well as the optical attenuator to attenuate the signal to the desired intensity level. And then she will send this signal to the quantum channel. And then in Bob's lab, he will have some laser source as the local oscillator, and as well as the balanced HOMODYNE detector to decode the signal. So there are several considerations in our experimental design. So for the first one is the local oscillator. So our protocol has the advantage that Alice and Bob does not need to share any phase reference. So Bob can put the local oscillator in his lab to avoid attack on the local oscillator. But if Alice and Bob use two different lasers, they will have a mismatch in the center frequency of the laser and also the finite line width. So this will cause some phase deviation between the early and late time bin, which is undesired, and it will degrade the performance of our system. So we need to characterize carefully and match as much as possible the frequency spectrum of Alice and Bob's laser, or use some locking technique to minimize the frequency difference, and as well as stabilize the frequency difference between Alice and Bob's laser. For example, using the technique shown in this slide. And then the next one is about the decoy state modulation. So the requirement on the ratio between the highest and the lowest intensity level of the decoy state intensity level is around 20 decibel. according to our numerical simulation, and this value can be achieved using commercial intensity modulator. And then the third one is about the mean photon number characterization. So there are three ways to do this. Alice can characterize her mean photon number using these three ways. So for the first one is using the energy estimation method using this equation for phase randomized coherent state. And then the second one is to use linear programming to bound the lower and the upper bound of the mean photon number. And then the last one is to pre-characterize the mean photon number using the single photon detector. So based on our observation, we observe that the first method have a bad accuracy if we go to the lower mean photon number. So the second and the third method is preferred. And then the last one is about the HOMODYNE bandwidth. So we desire to have a large bandwidth so that we have a higher speed, and we also minimize the phase deviation between the early and the late time bin. And our group is developing some high-speed HOMODYNE detector that shows good potential to be used in our experimental implementation. So this is the end of my presentation. Thank you and have a good day.